Okay, so let's start. Can you hear me up there? Okay, so let's start with registration. Who is not registered to the class? 1, 2. That's it. Only 2 of you are still not registered. I'm going to ask again, but last time for today. Who is not registered for the class? 2. Okay, so come to me after class. We can register you today. That's it, I guess. There are quite a few people on the waiting list, but I guess they don't want to be in the class, so there's room for you. So I think we'll be done with this saga quickly. Okay. First quiz was due last night. Hopefully all of you did it. Anyone did not know about it? Any questions, issues? Okay, excellent. So any questions on administration or any other things? Okay, so let's move on then. So, and again, I want to remind you, ask questions during class. Don't just come after it and ask questions that everyone else has. If you do have your own questions, about the material or anything else, office hours is the best time for that. But again, most of your questions are things that everyone cares about. So please ask during class. Okay, so where are we? So we are still introducing key issues in machine learning and using it as a way to talk about specific issues that are important. So we talked last time a lot about modeling. We talked about representation. Question? Yes, it's changed since last time. Yeah. So I'm going to change the slides a little bit before class and put it back online. So this version is not online yet because there's some SSH problem, but in principle, you have a default version of all the lectures that you'll see in the semester, but all of them will change. Mostly a little bit, some more, just before class. But it's still a good idea to look at it before, so it's not going to be a very significant change. Okay, so we talked about modeling and representation, and just toward the end of last time, we started to talk about the how to learn. And by the way, you will see, even in the first homework that is going to be out early next week, already issues that will force you again to think about modeling and force you to think about representations, features, and so on. So how do we learn? So we agreed last time that one possibility is to do what I call here a local search, guess a hyperplane, because we agreed that we're learning hyperplanes. Maybe it's a good time now at 10:37 to say that I'm always starting the class 3 minutes after 10:33, and I'm hoping that this gives you enough time to wake up, come to class. I think most of you don't have classes before, so please try to be here. You don't have to be here at 10:30, but 10:33, because it bothers me that many people come in after, and I'm sure it bothers you too. So please try to be here on time. Okay, we agree that local search is a good possibility, which means we're going to guess a hyperplane, and then we're going to try it on the data we have, see how well we're doing, and correct. Of course, there's a question of what does it mean to see how well we're doing, and there's going to be a question of how to correct. And these are really the key to questions that drive the algorithms. In order to talk about it, we introduced what we're doing. Basically, our goal now is to predict y based on an observed input x, or saying it another way, estimate a functional relationship f of x. And really, we're talking about classification. We're going to talk most of the class about just the 0-1 case. And we will see later on that once we do the 0-1 case, we actually have done all the discrete case, the multi-class classification case, where you have Cayley labels. Now, what do we really want to do? We want to be able to find a function that makes the smallest number of mistakes possible. And we're going to use this notion of risk and loss as a way to evaluate it. So one way to think about it is that we want to minimize this risk, which I'm defining here. So I have a predicate, f of x not equal to y. This could either be yes, true, or false. And I want to take the expectation over this. That's what I want to minimize. And one comment that we made at the end of last time is that really we don't know the distribution over x cross y. Otherwise, there was no learning problem. We would just do this. We would just take the argmax over the probability of the label given x, had we known this distribution. So we don't know this distribution, so let's erase this. Because we don't know this distribution, we cannot compute also the expectation over x cross y. What we're going to do is we're going to try to approximate it, and we're going to try to approximate it using the training data. So what we're trying to do is to minimize this L prime, which is the average over the training data of how many times f of x is different than y. And of course, we all agree intuitively at this point that maybe that's not good enough, because our goal is to do well on future data that we've never seen, yet we are estimating what to do on the empirical data that we do see. Eventually, we're going to try to show that under some reasonable condition, this is actually good enough. So that's one issue. The second issue is that often trying to do this is actually hard computationally. What do I mean by hard computationally? Let's assume that I have these red and purple points, trying to find the best linear function, and by best here, I define it to be the one line that minimizes the number of purple points that go to the red side, plus the number of red points that go to the purple side. This is NP-hard. And that's another reason why we actually are not going to try to do exactly this. What we're going to do is we're going to try to find another loss function that is easier to work with. Basically, that it's easier to use it as a driving force for the learning algorithm. Okay, so now there are many ways to define what is the loss of an algorithm. This is going to be a key issue that we're going to talk about for a few minutes now, but over the class. So the simplest one, as we said, is just a misclassification error. You're going to tell the algorithm you're losing 1 if you make a mistake, you're losing 0 if you didn't make a mistake. You can define another loss, which I call here the square loss, which is f of x minus y squared. That also says if f of x is equal to y, you made the right prediction, you lose 0. But as a function of the distance of f of x from y, you're going to lose more and more. It looks something like this. And you can define other things. For example, you can define an input dependent loss. So it's 0 if you got it right, but it's some function of x, c of x, otherwise. And you can do many other things, and as I said, we'll see. So So here is an example of a few loss functions. What we see here are 4 different colors, 4 different loss functions. I'm going to talk about 2 of them. So let's start with the black one. The black one is a step function. Below 0, the loss is 1. To the right of 0, the loss is 0. Now, notice that in order to put all these loss functions on the same plot, I had to redefine the x-axis. For the black curve, the x-axis is just the product y times f of x. Let's think a little bit about what does y times f of x mean. So y for me is the label, plus or minus 1. F of x is the output of my function, the prediction I'm making. Remember that we're making prediction with a linear function, dot product of w and x. So it's going to give me a real valued function. When is y times f of x positive? Yeah? When they have the same sign. So either y is plus 1 and f of x is positive, or y is minus 1, but f of x is negative. So basically, y times f of x is positive when the label and the prediction pretty much agree. Right? So therefore, the x-axis really here, the z, is really y times f of x. And you can see that for the black function, if there is agreement in the positive side of y times f of x, I lose nothing. If there is disagreement, y times f of x is negative, I'm losing 1. Okay? Now, mathematically, I'm defining it at the top there. It's a half of 1 minus the sine of y f of x. And notice here that the sine, I'm defining the sine here to be plus or minus 1, which is a little bit different than what I defined a few slides ago, just for convenience. But it's really, semantically, it's the same thing. If it's negative, if the function is negative, the sign is minus 1. If the function is positive, the sign is plus 1. So that's the step function, black. Let's look at the blue line. The blue line is a hinge loss. It's also an important loss function that we'll see. And what do we see there? We see there that above 1, where the z-axis here is above 1, we lose 0. If it's below 1, it goes linearly higher, and we're beginning to lose. Let's see, what does that mean? It means that if yf of x is 1 or more, remember that y is plus or minus 1. So f of x, if f of x is 1 or more, I lose nothing. If f of x is positive, but between 0 and 1, I started to lose. It's this region. And this loss goes linearly high as f of x becomes smaller and smaller. Okay? How do I write it? Mathematically, we're writing it here. Look at the third line. So it's the max between 0 and this. So look, think about this. It's 1 minus yf of x, which means that if yf of x is 1, this value is 0. This is exactly this point. If yf of x is greater than 1, which means f of x is very, very positive, then this term is going to become negative, but I take the max between it and 0. So it's all, I'm losing nothing, it's 0. And otherwise, if yf of x is less than 1, which starts from here, from this point to the left, I'm starting to lose. Okay? And it's linear with f of x. So that's going to be an important loss function. You can try to understand the other loss functions that are written here. The important thing is that this is how I tell my algorithm, how well are you doing on this example. Yes?
So y f of x is essentially just like a dot product. It's going to be large when your y's are 1 at the same time that your f of x is 1, right?
What you said at the end is perfectly correct. The way you started isn't. Why? It's not a dot product. What is y here? Just a number, a scalar. It's plus or minus 1 in my case. What is f of x? Also a number, right? It's the dot product, but it's a number. So these are scalars. So y of x is not a dot product, just a product of two numbers. Okay? But they indicate how well my function is doing relative to the label. Yeah?
Yeah, so we were talking last class about the problem of overfitting, and to avoid that, we decided sometimes you'll have to ignore extreme outliers. But it looks like with these loss functions, the more extreme the outlier, the more the algorithm feels like it's correct.
True, true. Good comment. So basically what we're saying here, if we are making big mistakes, we're suffering more. And we'll have to think about what impact does this have on the learning of the algorithm, whether it overfits more or less and so on. We'll get to this. Other questions? So the importance of this, I show you 4 different things. These are basically how we send messages to the algorithms. Are you doing well now or not? And we'll see how this drives the learning algorithm. So now we're going to put this together. Yes?
All of those functions on the theory side seem to almost disappear as z gets very large, except for the square loss. Does it still end up being functionally the same for us, or do we have to treat it differently?
Good point. So that means that the square loss is doing something wrong if we just treat it this way, because if it's very, very positive to the right side, we shouldn't lose intuitively. Nevertheless, with this function, we do. Yes? Okay. So now we have all the ingredients. Let's learn. So as we said, this is how we're going to learn. We addressed how well we are doing. We need to address how do we correct when we're not doing well to actually learn. So what we're going to learn is we're going to learn a linear function. I'm going to call this a linear threshold unit because really the function is dot product wx minus theta, and we're taking a sign of it, which is the threshold, right? We're saying if it's above 0, say 1. If it's below 0, say minus 1. That's the threshold. That's why it's called linear threshold unit. Now, before we start, I'm going to have, okay, so first notation. So x is going to be my feature set. We took data. We converted it to features. We talked about it last time. You're going to play with it in your homework. Now, I forgot about what the data is. I have a vector x that represents my input. W is going to be the vector that represents my function, the linear separator. And theta is the shift relative to the origin. Now, I don't want to carry this with me all the time. I want to simplify the representation. So we're going to do a canonical shift to the representation. Instead of talking about wx minus theta, I'm going to talk now about w prime dot product with x prime that has exactly the same value, because what I'm doing is I'm adding one dimension. Instead of talking about x, I'm adding one dimension of value minus 1 to each x. I'm going to call it x prime. I'm going to take w, add theta as the last dimension, call it w prime. And now you'll notice that w prime dot product x is exactly the same thing as w dot product x minus theta. Okay? So what does that mean? It means that when you get the data, you add minus 1 to the dimension, to the last dimension, as the last dimension. And now instead of n-dimensional problem, you learn n plus 1 dimensional problem, and you don't need to think about theta. Most algorithms are going to do this. It's easier to think about it this way. And basically, that means that when I'm learning w, I'm actually also learning theta. This is the n plus 1 dimension of my w vector. That's just notation, really. Okay, so now we can learn. So our goal is to find this w that minimizes a risk. Again, let's make sure that we have the right notation. So the risk is going to be the average or expectation with respect to x cross y of the loss on each example. So the loss, which I denote here Q, is a function of x, y, and w. I have w, and it tells me, relative to this w, how much did I lose when on this x I predicted y. And this happens for every point. So Q is a function of x, w, and y. And then I average it over all my data sets, and this is the risk or the error, which is a function of w, no longer a function of x and y. As we said, we cannot do it with the expectation, so we're doing it by averaging over the data set. Now I want to minimize this function. To find this minimum, I'm going to use a gradient descent algorithm, a batch gradient descent algorithm, that basically will allow me to walk over this error function until I get to a minimal point. So how do I do it? We estimate the optimal parameter w in this way. So at time t plus 1, I'm going to take the w that I had at time t and subtract the gradient of this error function. Or, I'm writing it here more explicitly, the gradient of this average over m points of the loss function. So really, we want to find a local minimum of the function. We're going to use gradient descent, which means that we're going to take steps proportional to the negative of the gradient of this function until we reach a minimum. You can think about this graphically this way. So this is, the x-axis here is w, the weight vector that we have, the function that we are learning. The error is a function of it. I'm drawing it somewhere here. And our goal is to try different w's until we reach a w that gives us a minimal value of E of w. How do we do it? We compute gradients, which are the tangents for this, and we walk down along this gradient. That's the algorithm. Okay, so how do we do it? So we're going to fix a loss function. The loss function in this exercise is going to be LMS, the square loss. And one reason is that it's very simple to work with and to compute gradients. Notice that I put half next to this function. It doesn't matter. If I minimize the dot product minus y square, I also minimize half of this, just for convenience, and you'll see in a second why. And we're going to minimize this function. So as we talk about how to do it, I want to introduce some more notations. So I'm going to use I as a subscript for vector components. We have vector x and vector w. I'm going to use j as a superscript, which is the time, the iteration number. And I'm going to use d to denote the example number. Okay, so let's assume the w superscript j is the current weight vector we have. Our prediction then on the dth example is just this, OD, which is the dot product wj transpose x. That's the prediction, right? Let's assume that TD is the truth for this target example. And therefore, the error is just summing over all the examples, TD, the truth, minus the prediction, OD, squared. That's it. Okay? So one way you may want to think about it is think about it as if there is some truth. I'm going to call it U here in this comment. This is the target weight vector. I don't know this target weight vector, but the target label is generated using this target weight vector. So TD is U dot product with X. Now, it's possible that there's some noise that was added So I'm not guaranteed that actually there is a function or there is a weight vector that is consistent with the data, but that shouldn't bother us. We assume for every x that we get the truth, and we learn relative to this, or we drive the learning algorithm relative to this, and this is how we drive it, right? We compute TD minus OD square, sum over all the data, and we define our error this way. Once we have a definition for an error or a risk, we try to minimize it. Okay, so how do we minimize it? We find the best direction in the weight vector W by computing the gradient of E relative to W. Yes? U is the truth. It's the true function that separates the data best. So I'm imagining there is this function just to tell you how did I get this T. Okay? But really we don't know U. And in real life, U may not exist, right? It's possible that the data is noisy enough so it's not consistent with any linear function. Okay, but I'm still imagining that this is how T was generated. Okay?
So error is the difference between the true function and function.
Yes. But a specific way of defining the error, right? So this way of defining the error, right? So for each example D, you give me the truth, T of D. You give me the prediction that my current function computes, and this is the error, okay? So it's true that it's the gap, the difference between truth and current prediction, but it's a very specific definition of how I measure this error. Yeah?
Is it fair to say you're setting this up quite similarly to linear regression and solving it in an optimized way?
Yes, it's very similar to linear regression. Only that my goal is somewhat different. My goal is I'm measuring this using error-driven algorithm. Yes.
What is J?
J is a superscript, it's the iteration. So I'm going to iterate, and I'll show you how I compute the W, my weight vector, in the J iteration as a function of the W that I had in the previous J minus 1 iteration. It's an iterative algorithm, right? I started with some W, I computed the error that this gave me, and updated W, J equal 1. And then I computed the error, updated W, J equal 2, and so on. Yes?
So in this case, I think you mentioned the square loss is not very good. So like, why don't you use the huge loss?
Because it's easier for me to compute derivatives relative to this. So we will use hinge loss. This is, one, it's easy. Two, it has historical value, because this is how people started to think about these kind of algorithms with respect to this loss function. Okay, so what do? We have this loss function. We want to compute gradient. This is the gradient. We differentiate E relative to W, which gives us a vector of the same dimension as W. And this vector specifies which direction we need to go in order to decrease W. We basically have to go in the direction of negative value of this gradient. So basically, W at time t is going to be W at time t minus 1 plus delta W, where delta W is the gradient of E times some step size, some constant R. That's the algorithm. Now let's compute the gradient. So as we said, E is defined to be sum over all data examples, TD minus OD square. I'm differentiating this. So I'm differentiating the sum over here. Can you see this red point? Barely, okay. And basically what I'm doing here is I'm pushing the derivative inside the linear sum. Here, you see why I put this half there. So differentiating this is basically 2 times TD minus OD, differentiating TD minus OD times XD. Remember, what was OD? It was a dot product, and therefore differentiating relative to one of the W's. All the other elements disappear, and all I have is just the coefficient differentiating this dot product WD times XD. I lost the transpose, but that's okay. And this is what I get, right? So I get TD minus OD from here. The 2 disappeared with the half. And from this dot product, when I'm differentiating relative to WI, all I'm left with is the ith component of the example. All the rest disappeared. Okay, so that's what I have. So basically, what I did is I computed what is the update rule. I computed what is the delta W. The delta W is sum over all the examples, TD minus OD times the XI of the dth example, multiplied by some step size R. So that's the gradient descent algorithm, right? So I started with some initial random weight vector. For every example whose target vector was TD, I computed OD, my prediction on the dth example, and then for all the examples together, I computed this data W and updated W accordingly. That's it. And we can continue until some stopping criteria. Stopping criteria can be the error is 0, which is rarely going to happen in real cases, or until E is below some threshold, or until E stops changing, or almost stops changing. So as you run it in practice, you will see that you have to think about what is the best stopping criteria for you. The important thing here is because I'm using this least mean square, this square loss, I'm guaranteed that the surface of the error function contains only one minimum, and therefore I'm guaranteed to converge to a weight vector that minimizes the error. That's the nice thing about this algorithm. So, of course, had I used a different loss function, this guarantee may not be there. And I may have multiple loss minima, and I'll have to deal with this. Okay, so that's algorithm 1, gradient descent. Algorithm 2, I'm going to call it incremental or stochastic gradient descent. Look at the update rule here. This is the delta W. This was the delta W before. What is the difference between gradient descent and stochastic gradient descent? Yeah? I lost the sum, you see? So here the delta W is defined for the dth example. Before, the delta W was defined by summing over all the examples that I had. Okay? So that's the key thing. So I dropped the averaging operation. Instead of computing the gradient correctly by averaging over all the examples that I have, what I'm doing here is I'm stochastically computing the gradient or sampling. Basically, by one example, I'm trying to estimate what would the gradient be. In practice, as I say it somewhere on this slide, people don't do it based on one example, but rather based on a few examples, small batches, just to get more stability. But basically, the idea is that we don't want for every update to touch all the data that we have. So the stochastic gradient descent algorithm is basically a much simpler algorithm. Again, I'm starting with an initial random weight vector. For every example, I'm computing, I take TD, which is the target value, I'm computing OD, and I'm updating W by incrementally adding data WI computed just for this example. And again, I'm continuing this until the error function, I'm happy with the performance of the error function. Either it's below some threshold or it doesn't change a lot. So in general, this algorithm isn't as stable as gradient descent. It does not have to converge to global minimum, but it's an online algorithm. Online in the sense that I take an example, I see how well I'm doing on it, and I update the W. As opposed to the previous one, that I have to first touch all the examples before I update the W. That's what I mean by online. Why is it, what kind of advantages do you see to online algorithms? Yeah? Much faster. If I have 100,000 examples, I don't really need to touch all the 100,000 examples in order to change the W. I can choose to look at one, or maybe I can choose to look at a few, just to get more stability to the gradient, but still I can run much, much faster.
If you do this over all of your data, does it converge to a similar value that your first LMS algorithm?
No. So the gradient that I computed are different. I changed the weight differently, right? So in principle, just the way it's written here, I'm not guaranteed to converge to the right thing. Now, there are many other tricks, and you will see some of them as we go. Basically, they have to do with changing the step size in a more interesting way, either with a fixed policy or with actually a policy that is data dependent. But this is the basic algorithm. All the other changes are going to be minor changes, and we'll get to them as we go during the semester. Yes?
Are you using the same random weight vector throughout the whole process, or is it randomized each time?
So I can, you have a database with all the examples, 100,000 examples. You can go one by one, or you can jump over this data. This really doesn't matter how you do it. But eventually, you want to be able to see all your data. The order, of course, matters, but you don't know ahead of time what impact the order will have. Okay, so basically, a little bit more on the learning rate R. It's important. We're going to later on talk about algorithms that deal with the learning rate in an interesting way. In principle, for stochastic gradient descent, R needs to go down in order to guarantee convergence. So what matters? The learning rate matters. The starting point, of course, matters, right? Because if you start very close to the minimum, you're going to learn quickly. If you start very far from the minimum, it may take a long time. But the important thing is that basically we learn two very simple learning algorithms, gradient descent and stochastic gradient descent. Almost all the algorithms that we're going to see this semester, whether it's linear functions or nonlinear functions, can be traced back to gradient descent algorithms. In fact, there will all be some version of gradient descent algorithms, either applied to more complex hypothesis space or just applied with somewhat different loss functions. And this is really a principle that goes back, if you want, to Newton many, many years ago. That's what we're still doing. Okay, so two last comments about this. There are many things we haven't addressed at all. For example, what we call sample complexity. How many examples do you need to see in order to make sure that what you've learned so far kind of makes sense? Again, remember that we do everything on the training data. We care not about the training data, we care about doing well on future data that we've never seen. And most of the data is future data, right? We talked a little bit about it. If you have 100 features, the number of examples, if we talk Boolean examples, over 100 features is 2 to the 100. You'll never see this many examples. You'll see a very, very small sample in your training data. So the question of how well will I do on the 2 to the 100 minus what I've seen in training data is really important. So how many examples do you need to see in training so that you can convince yourself that you're going to do well? So we can ask this question explicitly, and I'm going to ask it here without, and we're going to talk about it in more detail. So one way to think about it in a concrete way is to say, suppose I want to ensure that my function has an error rate epsilon, small epsilon, 10%, 5%, with high probability. So I'm pretty sure that the error is going to be less than 5%. So delta here might be 90% or 95%. How many examples do I need to see as a function of these small epsilon and delta? And you can show that this number of examples, m, scales inversely proportional to epsilon, and of course, inversely proportional to delta, although you can see here that delta goes in the log, which means it depends more on epsilon than on delta. And it scales linearly with n, which is the dimensionality that we have, how many features we have, which makes sense. If the problem has more features, it's a more complex problem, you should see more examples, to guarantee a certain performance. So we're going to actually deal with this a little bit later in the semester. I just want to tell you something about the fact that, it's actually an important question, right? You want to be able to know how many examples do I need to see. If I saw 100 examples and I have 100 features or 1,000 features or 1,000,000 features, can I say something sensible about my algorithm, the output of my algorithm? So that's one question. A second question, as computer scientists, we should care about computational complexity. Actually, it can be shown that there is a polynomial time algorithm that finds this consistent linear threshold unit. Basically, you can reduce this to linear programming, for those of you that know something about linear programming. But it still doesn't say how will an online algorithm, we talked about online algorithms here, or at least incremental algorithm, how long will they take to converge? If you see all the data at one time, like in a linear program, it's a polynomial time algorithm. But maybe it's enough for you to see the first 1,000 examples, and you're done, and you don't need to see the 100,000 examples. So what can we say about how long would it take an online algorithm to converge? So basically, the intuition here that I'm selling you now, and we're going to get to it later in the semester, is that these algorithms depend inversely on the margin, which is, hand-wavingly, the distance of the points from the true line, which again should make some sense to you if you go to look at this picture here. Our job here is to look at these data points and try to fit a line that separates red from purple. If the red and the purple points are very, very close together, it will take you a long time to try to figure out where to fit this separator. If they are very far apart, the purples are there, the red are there, any line that you'll put in the middle, just by looking at a few examples, will already do it. And therefore, this margin, this distance from the true line is kind of an important complexity parameter here. It really tells us how complex the problems are, and how long it will take us to learn this function. Okay. Yes.
So for the sample complexity thing, there need to be some additional parameters like constraints, right? For example, if I just take a US tagging problem, and if I just give one feature, which is the first word or something like that, even if I see infinite examples, I cannot have any guarantee.
Yeah, excellent. So basically, yeah, so what you're saying, maybe I cannot even express the correct function with this linear function. But my first bullet there is assume that the data is linearly separable. What does that mean? That's an important thing, and get used to this terminology also. So let's assume that I have the right representation, and with the features that I use to represent my x, my data, there exists a linear threshold function that separates purple from red. Now I can say what I said here. Otherwise, no. Okay, I have to say more things. But this is a reasonable assumption. In fact, it's a reasonable assumption given what we said last time, which is that every problem can become linear if I transform the space properly. And as we'll see, it's actually good enough even if we don't completely know how to separate the data, but we can approximately separate the data. We can relax these kind of results. Okay, finally, what I gave is a very generic way to learn linear threshold function. There are many, many other ways. Old ways like Fisher linear discriminant that basically is a direct computation method. You take data, you compute something, you get a separator. And in order to do this, this method makes even stronger assumption on how the data was generated. Or probabilistic method, like algorithms like naive Bayes that we're going to see in a few weeks. It produces a stochastic classifier, but really, it's a linear function. It's a linear threshold unit. Or algorithms that are important, and we'll see later on in the semester, like perceptron or Winnow, and many, many other, logistic regression, support vector machines. All these are linear threshold units representations, and the learning algorithm is somewhat different. At least when it was invented, it looked very different. We will show that actually they are very, very similar. In fact, small versions of what we've seen today. Okay, questions on this? Okay, so let's move on. And as I said, almost all the learning algorithms that we're going to see are very similar or derivative of linear threshold functions, except for what we're going to see today or now. And we're going to start by talking about decision trees. Okay. Okay, so basically, as I said, we talked about two very important examples of learning algorithms. Not the only algorithms. One question we can ask is, we learn a linear function, and in principle, the function may not be linear. This was the question that we just asked. In order to learn the linear function, really what we've done is we extracted features, we generated this vector x, and used it in our learning algorithm. Can we learn a function that is more flexible relative to the feature space? And of course, there's question 2 here. I'm going to leave it on the slides throughout the first half of the semester until we get to develop enough tools to actually answer it. So what have we done earlier today? We actually decoupled the generation of the feature space from learning. We said, here is data. We generated vectors, x. We gave this vector x to the learning algorithm. Can we do something else? I mean, in the first treatment that we had, we actually had to think about expressivity. Do we express the data in a good way. And then we gave this transformation idea that says even if it's not expressive enough, you can do something in order to make it expressive enough. In decision trees, we actually are going to think about it differently. We're going to basically start with the data and do learning directly from this data, where the algorithm chooses how to transform the data. We don't have to do something ahead of time. Of course, we need to tell it what it sees, and you're going to do this in your next problem set, because the data comes, says names. In the badges example, you still have to tell it, what do you see when you read names? Do you see characters? Do you see just tokens? Do you see length? You'll have to tell it what it sees, but from that on, the expressivity is dealt with by the algorithm itself. Okay, so that's one motivation to work on decision trees. There's another motivation, which is if someone asks you what's the best learning algorithm, of course, this is a very ill-defined problem because there's a question of, what type of data do you use, how much time you have, do you care about the type of output the algorithm produces, do you care about being able to interpret the output or not, and so on. But one reasonable answer to this question, despite the fact that in the media you've read that neural networks solved everything, is actually built on decision trees. I would argue that the best generic learning algorithm, if you know very little about the data, is to build an ensemble of decision trees. Basically, what we will call in a few weeks boosted decision trees. It's going to be a well-crafted linear model on top of features that each of them is a decision tree itself. And this is going to be a very, very good learning algorithm being used a lot commercially, and we will also play with it in the first problem set. Okay, so today we're going to start looking at decision trees. We're going to first understand what they are, and then provide an algorithm, and then talk a little bit about some overfitting issues and experimental issues in machine learning as introduced in general, but we're going to talk about them or introduce them in the context of decision trees. Okay, so let's first start by talking about representing data, which is one perspective of thinking about decision trees. So let's assume that you have a large table, n attributes, to describe some data. For example, you have information about people, and you know whether a person owns an expensive car or not. So you can represent a histogram. How many people own an expensive car, how many people don't. Now, let's assume that you want to represent more information. You want also to describe gender. So you want now to represent two attributes, which means you have 4 values. Male own, male doesn't, female own, female doesn't, and I don't know, it doesn't matter which is which here, but you will need to have a histogram with 4 of size 4. Now, if you have 16 attributes, the one histogram is going to be just 60 numbers, but if you want now to have conjunction of 2 attributes, already you have 16 choose 2 large histogram, 120. I don't have room on the slide to do it. If you want 3, combination of 3, 16 choose 3, even larger number, and so on. So basically, if you have 100 attributes, just for conjunction of 3 of the attributes, if you want to count how many people have this conjunction of 3 attributes, you need to have 161,000 numbers. Not a good way to represent your data. You will really have no idea what to do. And what do you want to do here? You want to be able to think about, okay, so what's important? I mean, maybe some of the attributes are meaningful, some of them are not. How do I represent it in such a way that actually reflects what's important in my data? So this is where information theory is going to help us. It's going to we're going to use some information theory principles in order to represent the data better. And the tool we're going to use is that of decision trees. So basically, decision tree is going to be a data structure that represents the data essentially by implementing divide and conquer strategy. It's non-parametric. All you have to get from this is there are no parameters here. We just have a representation. And you can think about it both as a classification method that is classifying elements into positive and negative, or as in this case here, to A, B, and C, 3 classes. But it can also be used as a regression method. So it will give you a number between -1 and 1 as a way to, for each item that you have. So basically, given a collection of examples, instead of a set of histograms that is going to be too large, we're going to learn a decision tree that represents this data. And once we have this decision tree, given a new item, we'll be able to classify it. So think about this set of data items that I have here. I already classified them into 3 classes, A, B, and C. And what we want is we want a compact representation of this, rather than just the list of these items. I want to be able to have this compact representation. And you can see that there's no one attribute that can help you to classify into A, B, and C. You have to look at it a little bit more carefully. For example, I can represent it this way. I can say, well, let's first look at the color. If the color happens to be red, it's B. If it happens to be blue, I have to look at the shape. It could be either A or B or C, and so on. So that's a decision tree. And I looked at 2 attributes, the color and the shape, and that allowed me to organize the data. Okay, so notice that what do I have here? I have 3 attributes. I have color, shape, and the label, Y. Color and shape have 3 values each. The label happens to also have 3 values. And that's the type of data that I want to represent. Yes?
How do you know to organize a tree so that you're looking at color first?
Good question. It's definitely not the only decision tree, right? You can easily come up with other decision trees. And I'm not even making a claim that this is the best decision tree. What is the best decision tree? Any suggestion? Yes?
Maybe the one with the fewest leaves.
Fewest leaves? Yes?
Smallest height.
Smallest height? Yeah. Some notion of small, right? That's your intuition. And clearly, I didn't show you that this is the best. It's a decision tree, and you can come up with others. So I'm hoping to get, at the end of this lecture, to thinking about this. But clearly, once I have this decision tree, you know how to evaluate it. By evaluate, I mean, if I give you a new item, you know how to classify it into A, B, and C by asking this question. First, asking about the color. As a function of that, asking about the shape, if needed. And what we want to know is how to learn this decision tree, how to take the data and induce a decision tree that is, let's say, good. It's not going to be best. And we're going to justify why not best. Okay, so first of all, I want to talk about expressivity a little bit. So I changed from A, B, and C to pluses and minuses because it's easier to think about Boolean functions. Everything we say about Boolean function can be said about any discrete value function. And I want to argue that decision trees are very, very expressive. That is, every Boolean function can be represented as a decision tree. I'm proving it by example here, but you will think a little bit about it and prove it to yourself. For example, every disjunctive normal form can be written as a decision tree by taking every conjunct to be a path from root only to the leaves, the way I've written it here. One path is green and square. Another one, it leads to a positive. One path is blue and circle. And one path is blue and square. These are the positive examples. The rest is negative. So basically what I describe here is a DNF. And you can always do this when you have a decision tree. All Boolean function can be represented. Now, if you think about it, only in this kind of case, when we have 2 dimensions, each one of them has 3 values, 3 colors, 3 shapes. The size of x, the size of our instance space, therefore, is 9, right? 3 times 3. And the number of Boolean functions on this, Boolean function because I changed the y to be only pluses or minuses, is 2 to the 9. So they are very small, but still there are 512 possible functions. All of them can be written as decision trees. We only learned 1. Or we show you 1. Yeah. So again, the function space we're talking about are really large. Okay, so what is decision tree? Decision tree is this data structure where the output for us is going to be discrete categories. There are good algorithms. We're going to give a generic algorithm. There are some bells and whistles that people have added to this generic algorithm. But they're very efficient in processing large amount of data. They're not as efficient in other algorithms when they have a lot of features, but this won't bother us. And we're going to talk about next time about various methods to relax or to augment the basic algorithm to deal with noise and to deal with missing values and a few other important extensions. So one thing to keep in mind is that even though the output is discrete, the input does not have to be discrete. There are many ways to deal with real valued x's. And this is one simple way, right? So I can basically condition on x being greater than 3 or less than 3 or, for each one of the features. And this way I have decision nodes in the decision tree. So it doesn't have to be discrete value also for the attributes. Okay. So as I said, I want to get to algorithms. And in order to get to algorithms, we're going to start looking at data and decide what to do. So here is a decision tree. You can agree with me that evaluating it is very easy, right? If you give you a data item, you can just go down the tree and compute it. And the question is going to be how to learn a good representation for it. Here is the game that we're going to play as an exercise to learn a decision tree. The decision problem is going to be, will I play tennis today? We're going to have 4 features: outlook, temperature, humidity, and wind, and 2 labels. So the data is going to look like this. Okay? I use shortcuts. So I have 14 examples. Look at the data. I have 5 negative examples, 9 positive examples. And the goal is to take this data with these 4 attributes and try to learn a decision tree. How would you do it? Ideas? Yes?
Take each variable and use it as a binary classifier and see how good you are. And then choose the top of your decision tree as the variable which is the lowest error rate. And then repeat the process for all the variables.
Okay, so basically what you said is 2 things. The second thing you said, I need an iterative algorithm, right? I need to choose the root. And once I chose the root and I split the data based on this root, I can keep on going. We're going to do that. The first thing you said, you actually gave us suggestions for how to choose the root, because that's really the basic decision here, right? So when we come up with an algorithm, we agree that it's going to be recursive. And the key step to think about is exactly the way you started, which is which one is going to be the root. Once you have a good way to decide on the root, we're going to choose the root, and then we're going to keep on doing the same, using the same principle when we choose the next steps. Okay, so And that's actually exactly what we're going to do. Here is an algorithm. I'm just writing this recursive algorithm. It's very simple. We're going to start with a set S of examples. We have label and we have attributes. And we're going to run an algorithm that we call ID3 over S, attributes, and label. Now, if all the examples are labeled the same, return a single node with this label. Otherwise, it becomes interesting. Let A be the attribute that best classify S, right? So I'm choosing the best attribute. I create a root node for the tree. For each possible value V of A, I'm going to split now, add a new tree branch for A equal V, and now I'm going to continue. First of all, I'm generating a new data set for each branch. SV is going to be the subset of the data set for all the examples for which A is equal V. So in this case, I chose Outlook. It has three values, sunny, overcast, and rain. I have now S sunny, which is all the example for which Outlook is sunny. Then I have S overcast and S rain, three disjoint sets. And I'm going to continue and do the same thing for this SV. SV is the subset of the examples with A equal V. If it's empty, I'm just adding a leaf node with something. Otherwise, I'm continuing, and now I'm running this ID3 with the set SV instead of S that was in the top, with all the attributes but for A, and with the set of labels. Basically, a recursive algorithm. So the key decision is, I'm going to skip this. The key decision is how to choose the root attribute. And our goal, as you all articulated, is I want something small. It turns out that finding the minimal decision trees, under almost any definition of minimal, height, number of nodes, it's NP hard. So what we're going to do is we're going to run a heuristics, a greedy heuristics, that is going to do well, but will not find in general the minimal decision tree. So as a puzzle to leave you with, let's think about what is the best way to pick a root attribute. And I'm going to give you this data set, very simplified data set. I have two attributes, A and B. I have 50 examples, 0, 0. I have 50 examples, 0, 1. All are negative. I have no examples, 1, 0. And I have 100 examples, 1, 1, and they are positive. What's the root attribute? Or what would you choose as your root attribute? Yes?
Would we calculate the entropy of each one and select the best?
I don't know what's entropy. Maybe next time we'll know what's entropy. But now, give me an intuition. Which one do you want to choose, A or B? Yeah.
The highest one, A. I mean the 100 example one.
The one with the 100 example is, what do you mean with the 100 example?
So you could split the maximum number of examples in the first.
So which one do you choose at the top? No, but you have to choose an attribute, right? So it's not based on example. You're choosing a conjunction, A equal 1 and B equal 1, but I need just to choose an attribute. Suggest an B over there.
I also said B
Why?
because I guess when B equals 1, we have the most number of examples.
150 examples, and then checking A equal to 1 more classify 100 examples.
Okay, another suggestion.
If A equals 1, then we know it's positive because nothing, no case when if A equals 1, there's no examples.
Okay, so basically there's some disagreement. If I split on A, I'm going to see something like this, right? If A is 1, I know that it's positive, right? If A is 0, I know that it's negative. If I split on B, if B is 1, I still need to ask what A is. Right? So which one should I choose in this case? I should choose A. And again, the reason is that I'm closer to the end this way, right? Or if you want, on average, I will have to ask less questions. But I can make a change here, right? So, okay, this is just summary of what we said. Splitting on A, we get purely labeled nodes. Splitting on B, we don't get purely labeled nodes. What if I change the data set a little bit? And in the case A equal 1, B equals 0, now I have 3 negative examples instead of 0. Now, the dilemma here is that now I will not get purely labeled nodes when I split on A. So the structure of the tree is going to be exactly the same whether I start with A or whether I start with B. Draw it to yourself. We're going to do it next time. So now the question of whether it's A or B isn't as easy, and we have to come up with some mathematical notion, maybe we're going to call it entropy, that will help us decide. But think a little bit about it and convince yourself. We're going to start from this next time. Okay, see you Wednesday then. Oh, the 2 people that are on the waiting list, come to me now. Yes. You are on the waiting list. Okay, actually, I want to write your name. Why did I do this? So how long have you been on the waiting list? What's your name?
My first name is XIAOT.
And your email? Okay. That's it? Okay, good. And how long have you been on the waiting list? You know?
Maybe about
Okay. So all of you are on the waiting list?
I am.
You are. So when I asked people, there were only 2, and now a few more were born. What happened? So did you?
He said he will send me.
Just a second. When I asked at the beginning of the class who is on the waiting list, you said yes. You said yes.
Me. I raised my hand.
You raised your hand. And what about you?
we are actually like at the corner, so.
So you were not here yet. Okay. Let's just deal with waiting list, not deal with other things. Your name?
Troyan. ZHUO.
ZHUO.
YANG. Wang. WANG.
And email?
It's A instead of I. Yeah.
Yeah. This?
Yeah. And my email is Wang, my last name, ZY,
ZY.
at SAS.UK.
SAS. Okay. Number 3.
Faraz, Faraz. The last name is Amzajarian, AMZAJERDI. A-N.
Okay, so we'll check if it's correct.
Yeah.
An email,
F-A-R-A-Z-A at cis.upenn.edu.
Okay, good. So all of you should get this afternoon email and that you can get into the class and try to register as soon as you can. Number 4.
My name is S-I-Y-U-A-N-G.
Yes, slower.
S-I-Y-U-A-N-G. G-A-O. My first name is S-I-Y-U-A-N.
Oh, sorry.
Oh.
Yes, like this.
Oh, no, S-I-Y-U-A-N is my first name. And my last name is G-A-O.
G-A-O.
Yeah.
That's it?
Yeah, that's it.
Email?
S-I-Y-U-A-N-G at cstate.upenn.edu.
It's okay?
Yeah.
Okay.
Yeah, thanks.
And my name is Lori Wang, L-U-O-R-I-L-I. Wang, W-N-G. My family name. And Leah, L-E-A-W-N-G at ses.upenn.com.
Okay, something is wrong here. So the first name is correct?
Actually, yeah. And this is my email. Yeah.
So how come this is L-U and this is L-E?
Just this is my real Chinese name, and this is my English name.
Okay, so it's L-E-A-W-N-G?
A-N-G.
A-N-G.
A-N-G. Yeah.
At cis.
Yeah. It's small L.
Yeah, that doesn't matter, but we'll change it. Okay.
Yeah, I'm Tianyi Zhang, T-I-A-N.
P-I.
T. Yeah, T-I-A-N.
I-A-N.
Y-I.
Y-I.
V-H-A-N-G.
V. Z.
Yeah. H-A-N-G. Yeah. And my email address is ZTY. Yeah. At.
Oh, wow, simple.
No. GSE.
G.
S-E.
What is this?
Education.
Graduate School of Education. Okay,
Yeah.
upenn.edu. Correct?
Yeah.
Okay, excellent.
Thank you.
You are not waiting list.
I just had a doubt.
Yeah, okay, so just give me a second.
Yeah.
And after we have registered, can I make up everything? I mean, the homework and the quiz and everything?
You should have done the quizzes already.
Okay, yeah, got it.
And homework 0 you've done?
I didn't do the quiz one.
Okay, homework 0?
Yeah.
Okay. Quiz 1 is less important. Homework 0 is more important.
So can I make up the homework 0?
You should do it today.
Okay, yeah, sure.
If you haven't done it.
Yeah.
And email it to Hang Feng, the head TA.
Okay.
Yeah.
And can you upload your slides on the web page?
It's already there.
Not on the Canvas, the web page.
It's already there. It's been there for a few weeks.
I cannot
I
click that
can
one.
find the...
Go to the web page.
No decision tree, but...
No, decision tree is there. Everything is there. Go to the web page. I'll show you. You should be able to find it yourself, but here, you go to the web page. Oh, no internet here. Just a second. Okay, I won't do it now because I have to log in, but basically go to the web page of the class. At the top you'll see syllabus.
Yeah.
And you'll find all the lectures.
It cannot be clicked, and there is no PPT or PDF for the lecture today. And after that,
Someone said that they used it. I'll check it, but I think it should be there.
this one, I think it's for today, right? Yeah. I guess. Yeah.
Can I find the decision tree?
I think the lecture slide is this one, September 16th.
Oh,
There is no
that's the same
slide
thing. That
here.
is the same thing.
But
It's the
when I
same?
Yeah.
check it, I cannot find the, this
This-
is slide for the last.
That's up to
semester.
78 or something like that. No, it's for, there's for fall 2019.
Which are you looking at? Which web page
We
are you
can-
looking at?
Yeah,
There is fall 2018 and fall 2019.
No, look at 19, not at 18.
Yeah.
is that this web page? So,
Yeah, this is correct. This is correct. Fall 2019 is right.
Wow.
It's right.
It's right?
Yeah, fall 2019 is
Yeah,
right.
but
Yeah, so this introduction thing,
mhm.
it's
Yeah.
it covers what we covered today, except the decision
Like-
points.
there is no slide, like, this slide is for
Okay.
the last class.
Maybe I
think.
just
Yeah. When I
Yeah, but it's including also this class.
It includes this class. I think it's up to 70 something is there, 78 or
Yeah,
something.
72 or something. Yeah, it's everything.
I see.
Yeah.
Thank you.
Yeah, and it's probably better to look at the PowerPoint than the
Mm-hmm.
PDF.
Yeah.
And also the decision trees should be there, but we'll see. Yeah, you had a question?
Yes.
Thank you.
Sure.
So in the stochastic gradient descent algorithm,
Yeah.
you said we take up one example, we update the date on one example,
Yeah.
then go to the next example. So while we do this iteratively across examples, suppose for the first example we calculate the first weight. I mean, we calculate one set of weights, right?
Yeah.
Now as we move to the next example, that same weight what we calculated, that gets updated?
Yeah, you have a weight vector, and when you go to the next example, you use this as your W and you update it.
Ah, okay. I thought we calculated another set of weight. No, I get what you're saying.
Yeah. So there's the way I've written it is WT plus 1 equal WT plus delta W.
Oh, okay. The previous weight gets updated.
Yes.
And in reality, we take a batch of data and we do this thing.
In reality, you'll take, say, 10 examples and do it for 10, average of 10, rather than one by one. Yeah.
Okay. And then you also address this thing like how many examples we need to see in order to update this with some
Yes.
O notation with that delta and epsilon.
Right.
That O is big O or
It's bigger, yeah.
that's big O?
Yeah.
Okay.
But this is something that I just made as a comment, you know. Really, we will see this in more details as we go. I just wanted
Sir,
to...
and in this particular slide, I think this is a small error. I'm not sure if it is my mistake or not.
Yeah.
If we split on A, if A is equal to 1, there is still positive and negative, so we need to ask B, right?
No. If A is equal 1, there's 0 or negative.
Oh, 0
100.
examples.
Yeah.
Okay, fine. That's how it is. Okay. Right. But then if it had been some examples, then again we have to split on
Yeah,
B.
right. So this is what I added at the end. What happens if we have 3 examples in this category of 1, 0? Now I have to split.
Oh,
And now the structure is going to be the same, and you have to think a little bit harder.
and that's where that concept of entropy and all.
Yes, this is where it's going to come in.
Okay. Thank you, sir.
Okay, sure.